welcome everyone. It's wonderful to have you here. I'm Mandana Khalili. I'm professor of medicine and director of the UCSF Research Coordinating Center's Investigator Development Unit of our NIMHD, Multiple Chronic Diseases Consortium, or HEAN network. I'd like to welcome you to our monthly training webinar. Before we start, we would like to acknowledge the Ramaytush Ohlone people who are the traditional custodians of this land. We pay our respects to the Ramaytush Ohlone elders, past, present, and future, who call this place the land that UCSF sits upon their home. We're proud to continue their tradition of coming together and growing as a community. We thank the Ramaytush Ohlone community for their stewardship and support, and we look forward to strengthening our ties as we continue our relationship of mutual respect and understanding. Excellent. Well, today we are honored to have our very own Dr. Tor Nealons speak to us about introduction to mediation and moderation methods and concepts. Dr. Nealons is a professor at the University of California, San Francisco, Division of Prevention Sciences in the Department of Medicine. His methodological areas of interest are multivariate statistical models with a special interest in latent variable models for survey scale development and validation, and mixed effects models for clustered and longitudinal data, including dyadic data. Dr. Nealons is particularly interested in training the next generation of prevention researchers working with minorities and marginalized communities. He's a PI of 2 NIH-sponsored R21 research education grants to foster grant writing and related research capacity building for early-stage investigators working with minority communities to prevent spread of HIV/AIDS and STIs, and to improve the lives of those living with HIV. Dr. Nealons also actively collaborates as a senior statistician and quantitative methods co-investigator on multiple prevention research projects, including our HEAN network. He is a co-author of the primer of applied regression and analysis variance book. Needless to say, we are incredibly excited to have his expertise today. Dr. Nealon, we looked forward to your presentation, and we appreciate the audience if they could put their questions in the chat during the presentation, and we'd be happy to address them at the end of the presentation. Dr. Nealon?
Thank you, Mandana, for that very nice introduction, and big thanks to Rochelle for all the work behind the scenes to set this up and get us here today. I'm going to go ahead and share my title slide, and it'd be helpful for folks to let me know with maybe a thumbs up if you all can see it. Okay, great. All right. Thank you very much for having me today. I know there's a DPS town hall running concurrently, and I recognize several of you from the DPS. And so let me just say that I'm very flattered and grateful you're making the time to be here. And I know Rochelle is going to be recording the town hall. So for those who can't make the town hall, they can watch it who are within the division, I think, at least. So that's good. So thank you, Rochelle, for that as well. So I'm here to speak with you this morning about mediation and moderation concepts and methods. And this presentation grew out of one that I did for the Center for Aging and Diverse Communities a couple of years ago, because scholars would often ask, what is this mediation versus moderation thing? And I always, never sure which one is which, and what does mediation mean and what does moderation mean? And so, as with so many things in statistics and biostatistics, the terminology can sometimes be a little confusing and maybe obfuscate more than clarify sometimes. So hopefully today's talk will help untangle some of those terminological knots. And basically what I have is around 45 slides. The last time I did this presentation, it ran for about 55 minutes. So when Rochelle asked me if I'd prefer an hour and a half, I said, let's go with an hour and a half to allow some time for questions and answers at the end. I have added a few more slides based on a course that I took back in August. So I'm guessing this is probably going to run around maybe 60 minutes, just to give you a feel for what we're looking at in terms of timeline here. Oh, you're not advancing. Why are you not advancing? Well, that's not what I wanted to do. Let's see. Just bear with me one moment. Okay, looks like I need to advance on a separate screen, so that'll be interesting. So today, the goals of the talk are to introduce the concepts of statistical mediation and methods that we would use for assessing it, and then introduce the concept of statistical moderation, different types of moderation, and some limitations of moderation analyses. What today's talk won't provide is an in-depth guidance on how to perform mediation and moderation analyses and how to interpret the results. So no software demos, no in-depth dive into results interpretation, because we don't have the time to do that. But what I will do is point you, especially at the end, towards some additional resources that you can use to learn more about mediation and moderation, including how to actually perform the analyses, how to pull the levers, and how to interpret the results. So let's begin with considering what is statistical mediation. So we might consider an exposure variable X and an outcome variable Y. And a typical research question might ask, what is the effect of X on Y? Or does X affect Y significantly? And visually, we can depict it in the way I have here. I hope you all can see my mouse pointer. We have this outcome Y, and we regress it onto X, and the coefficient estimate of that regression is little c. And little c, we will label in this area the total effect of X on Y. Now, that's all well and good if all we have is X and Y to work with, but what if we thought that X affected something else that in turn affected Y, that could explain that X to Y association? And so we see this a lot in intervention research, where we're seeking to understand why an intervention worked in terms of changing some level of a health outcome. So that's where mediation analysis is often used, although it can also be used with observational data as well. Oh, okay, I can scroll. Great, that makes me happy. So the most common mediation model is called a sequential mediation model. And the way it works is we introduce a new variable that we're going to call capital M that's caused by X and in turn causes Y. And in doing this, we implicitly assume that X precedes M and that M precedes Y. In other words, that we have some kind of temporal ordering, that the exposure happens first, then you have the mediator, and then you have the outcome. Now, we have a couple of figures over here on the right-hand side of the slide. The first one is simply a replication of what we saw in the last slide, and that is X leading to Y when we don't have M as part of the system of variables. And then we have this lowercase c here being the total effect of X upon Y. Now, if we introduce M, we often see mediation represented in a diagram like this, where you have X causing M, and the regression coefficient associated with that pathway is little a. And then you also have M causing Y, and that regression coefficient for that pathway is represented by little b. Now, up here, when you look at the X to Y relationship, because we've included M in the model now, that relationship will change. And so we need to refer to it by a new symbol, and we therefore refer to it as C prime. And in this particular setup, C prime is referred to as the direct effect of X on Y. A is the direct effect of X on M, and B is the direct effect of M on Y. So as I mentioned, this is known as a sequential mediation model. And let's take a quick look at some of the assumptions underlying the model, and then introduce a hypothetical example to help concretize the principles. So this is a very text-heavy slide, and as I was mentioning to Mandana and Rochelle at the outset, I developed my slides to basically be able to stand alone, so that if someone were to look at these later without having seen the recording of the presentation, they'd be able to read the slides and get a pretty good grasp of what is trying to be conveyed here. So I apologize for it maybe being a little bit tedious, but we'll have some figures and diagrams throughout that'll hopefully break up the text tedium a little bit here. This particular information comes from David Kenny's website, which is excellent. David Kenny is one of the forefathers of mediation analysis dating back to the 1970s. So he has a very extensive website. And for the sequential mediation model, if we're willing to assume that both M and Y are continuous, normally distributed variables, and that we model them using a linear regression approach, the coefficients for the total effect C and the pathway from X to M, that is A, those two effects are estimated under the usual linear regression modeling assumptions: normality of the errors, constant variance of the errors across levels of the predicted values, and linearity of the associations. However, the direct effect C prime and any mediation effects require additional strong assumptions, which I've numbered here. So one of them is that there's no X with M interaction. So no interaction between the exposure and the mediator. A second assumption is that there's temporal ordering, and we talked about that one on the last slide. X leads to M and M leads to Y, but no reversing of that ordering allowed. And this will come up again when we touch on longitudinal data. The third assumption is no confounding of the X to M association, nor the M to Y association. And because I'm old enough to have gotten my graduate degree before the Civil War, I remember back in the 1980s, like nobody, 1990s, early 1990s, nobody really talked about this, but it's been talked about a lot in the past decade or so. So we're seeing some movement and some progress on addressing that assumption. Number 4 is an interesting assumption, and that is that the mediator M is measured without any error. In other words, M has perfect reliability. Now, that is an assumption. It's probably not true most of the time, but often we conduct mediation analyses assuming it's true. As Dave Kenny points out, this phenomenon is generally underappreciated in the newer causal mediation literature, although there is an exception from 2012. Tyler Vanderweel and colleagues published a paper talking about some potential methods that can be used in the causal inference or causal mediation space to try to address unreliability of the mediator, but often it is not discussed. Now, the good news is causal inference methods, which we'll talk about a little bit later, can address the first and the third assumptions. So no XM interaction, no confounding of X to M and M to Y. And then latent variable methods can address assumption number 4, perfect reliability of the mediator. So let's talk about sequential mediation in terms of an example, because I think this can make this a little bit more concrete. So I took a simplified example from Aidan Scheim and Greta Bauer's 2019 paper, where they were interested in looking at whether experiences of discrimination mediated an association between race, ethnicity, and psychological distress. And in their paper, they had a lot of different levels of race and ethnicity. I simplified it here to just have 2 levels. And the question really here is, could people's experiences of discrimination explain or account for a previously observed link between non-white race, ethnicity, and distress? So, originally there was some kind of association between race, ethnicity, and distress, and they were really interested in seeing, well, if you include a measure of discrimination experience, say like the intersectionality discrimination index, otherwise known as INDI, can that explain this association that was observed previously? So to investigate that question, I think it's useful to take a little tour of the history of mediation. And We'll begin with what I'm labeling mediation 1.0, which is the 4 causal steps method. And in a nutshell, what the 4 causal steps method does is it uses a sequence of 3 linear regression models to estimate the mediation effects. And this was presented in Ruben Barron and Dave Kenny's 1986 paper in Personality and Social Psychology journal. And this basically says in the first step, you estimate the direct effect of X on M. So that's up here, X going to M. So you're basically estimating that A pathway. So in our little example, we're estimating the effect of non-white race ethnicity on discrimination experiences. Then in a second step, you estimate the total effect of X on Y. So that's C in that original model. So we're estimating the effect of non-white race ethnicity on psychological distress without the mediator present. But we're not done yet. So we have still 2 more steps. So the third step, we estimate the direct effect of X, that's C prime, and the direct effect of M on Y, that's little b. So that's the effect here of down here, discrimination experiences, coefficient B on psychological distress, but we're also estimating in that model C prime, the effect of non-white race ethnicity on psychological distress. And then in step 4, what you do is you collect all the results from those 3 regression models, and you step back and you assess whether mediation is occurring. And to evaluate this, you look and you see, do the direct effects of X on M, that's A, and M on Y, B, are those 2 things significant? So in other words, is there a significant effect here? And is there a significant effect here? And you can see that that's very logical, right? I mean, you want race ethnicity to be affecting discrimination experiences, and you want discrimination experiences to be affecting psychological distress to indicate that there's some kind of chain of effect here, or flow of effect going from non-white race ethnicity through discrimination experiences to psychological distress. All right, so then you ask yourself, does the total effect C from X to Y in that first model, if that is significant, but now the direct effect C prime, this thing up here, from the X plus M leading to Y model, if that is non-significant, then it is concluded that M completely mediates the original X to Y association, right? So the logic here is you started out with a significant X to Y relationship, but when you put M in the model, now the C prime effect, if it gets small and non-significant, that's indicating that the variance in Y is pretty much being explained by this causal flow here that's going through M, not this direct link between X to Y. Now, it's also possible that this total effect C in the original up here, X leading to Y, but no M, that is significant. And then when you introduce M into the model, C prime is still significant, but maybe the size of the effect is smaller, but still significant. So when the effect goes away for C, when it goes away completely, we refer to that as complete mediation. But when C prime, the direct effect of, say, non-white race ethnicity on psych distress with the mediation in the model, mediator in the model, if that is still significant, just reduced in size, we say that the mediator M here, discrimination experiences, partly mediates the X to Y association. So that has been used for quite some time. People still use this complete and partial mediation terminology. There are some methodologists who don't like that idea, and the logic is dual-fold. Hayes and Rockwood are a really good example of this. The first thing they point out is that in a smaller sample, the C prime effect is more likely to become non-significant. And yet in a smaller sample, it is likely to be estimated with less precision. The more cases you have, the more precision you have to estimate an effect, but the more likely you are to show a statistically significant effect. So they say that's then like, you know, a little inconsistent. And then the second reason they provide, which is that when you introduce a mediator M, there might be other mediators here that we haven't examined yet. And what if one of them were to make the C prime effect non-significant? So to say that something completely mediates the association doesn't really allow for the potential to have multiple mediators. If you have multiple mediators that can completely mediate the original X to Y association, that may be kind of inconsistent with this idea that your original mediator completely mediated the X to Y association. So it's kind of like, you know, if you write up a set of results and you say, well, as soon as I introduced my first mediator into the model, the X to Y association is now completely explained. Well, and if you're able to do the same thing with another mediator, then there is a kind of philosophical inconsistency there. So, you know, people are maybe moving off this complete partial mediation way of framing results for mediation analysis, but you still see it sometimes, depending on, you know, the disciplinary training that someone's had and who they're working with. But I wanted to present both sides of the argument for you. So.
Tor, I apologize. Yeah. There's a quick question that I think it's relevant for us to address. When you are indicating that when M is put in the model, you're meaning that it's adjusted for in the model, correct?
That is correct. That's right. Yes. A regression model that contains both X and M as predictors. Great question. Yeah, if there's clarifying questions like that, feel free to interrupt. Thanks, Mandana. Okay, so let's move to the next logical part of this, which is, so if we've established mediation, let's say, and however we want to do it, we then might want to quantify the amount of mediation that happened. And one way we could do that is we could subtract C prime from C. So remember up here, C is the original, to use the language of the questioner in the chat, the unadjusted model, right? You just have X in here. And then when you put in M, you get C prime because now the coefficient from X to Y is adjusted for the presence of M in the model. And so what you could do is you could take C and you could subtract off C prime from C. And that is known as the difference method. And so what's left over, once you subtracted off this direct effect, what's left over is the mediation effect. And we actually see people in the causal inference discipline use that definition for the mediated effect, maybe more so than in the traditional mediation literature. What's used more in the traditional mediation literature is you can multiply A times B to get the mediated effect, and that is what's known as the product method instead. And so there's an identity here. So in this next to last bullet, I ask, why can you use A times B to represent that mediated effect? Well, it turns out that in a linear regression model, the total effect of X on Y, that C up here, it can be decomposed into C equals A times B plus C prime from over here, here, here. And then if you do a little algebra and you just move C prime over to the left-hand side of the equal sign, excuse me, you get C minus C prime equals A times B. And that's the effect of the mediation. And we often refer to that as the indirect effect of X on Y through M. So again, this idea of a causal flow that's going from X down to M and then from M up to Y.
Or I'm so sorry.
Yeah, no problem.
One additional question, I think it's relevant. Dr. Danish, do you want to just ask that question yourself so that you can have that clarification?
As far as I know, when we have a moderator in a model, we cannot adjust the model based on the moderator. Is it a strategy that we can identify that as a factor is a moderator we are doing the adjustment, or there is something else that I don't know about that?
Well, we're not talking about moderation yet, but we'll talk about moderation a little bit later. But maybe you're asking about the mediator.
Mediator, I'm sorry.
Yeah, no
I'm sorry.
problem.
Yeah,
No
yeah,
worries.
you're right.
So you're saying when we have a mediator in the model, can we not adjust the model? We cannot adjust the model. You're saying it's a strategy to identify it. Yes, and this is a traditional methodology. It is, as I'm going to show in a few minutes, it's not actually used a lot anymore because of certain practical issues around different sample sizes for the different regression equations and that sort of thing.
Thank you.
Okay, great. So with respect to the indirect effect, then, for logistic, multi-level, and other models, that identity breaks down that I showed on the previous slide. A times B only approximately equals C minus C prime. So A times B is more often used to quantify the indirect effect than C minus C prime, at least in the traditional mediation framework. Now, there are several methods for testing the significance of the A by B indirect effect. I provide a reference in here to Steve Gregorich's 2014 A mediation talk for the CADC, which is online. I won't belabor the specific ones. I will just point out that the distribution of an A times B product is asymmetric, and so we need methods to get the significance of the effect that respect that asymmetry of the distribution. One of those is the non-parametric bootstrap, which I will mention in a few slides here. So I think I covered that last point already about products of coefficients, so I'll move on. So I wanted to wrap up this part of the presentation by just making a few comments about the impact and the limitations of this causal steps method. Tyler Vanderweel, who's at Harvard, who's an internationally respected expert on mediation analysis, has pointed out that the Barron and Kenny 1986 paper has been cited over 90,000 times. So it's had a huge impact in many fields. And I like to think of it as I said earlier, as this as being mediation approach 1.0. But as I also mentioned a few moments ago, it does have some significant limitations. For instance, for one thing, the samples assume to be the same for all three of these models. And often in real world applications, we have missing data, right? So we may not have the same N for the X to M regression and the X to M plus Y regression and the X to Y regression. And that's a problem, right? Because we really want to be using the same sample to come up with our results, not being reliant on different samples for different pieces of that mediation model. And then computing asymmetric confidence intervals for the indirect effect is not built into most regression software routines because they weren't built to do mediation analysis. They were built to do regression. And the other thing is it's pretty easy to fit using the causal steps method if all you have is one X, one M, and one Y. But more complex models where maybe you have X leading to M1 and M1 leading to M2 and M2 leading to Y, those are going to be a lot harder to fit. Some of them may be like really kind of practically impossible to fit. So what do? Well, due to the limitations here in the 1990s, structural equation modeling, SEM, became popular for testing mediation. And structural equation modeling, I think this application for mediation occurred partly because computers became powerful enough to fit structural equation models in general, and structural equation modelers realized that they could use SEM to fit and investigate mediation models. And the key thing to understand about SEM is that it's a simultaneous equation estimation method, meaning it can estimate all pathways simultaneously. And it's often done using maximum likelihood estimation. But there are other estimators you can use. I like to view SEM as mediation version 2.0 when we use it to investigate mediation questions. And it has several advantages. So let me just walk through those. One is that it can estimate each of the mediation equations simultaneously. So this eliminates this problem of different n's being used to estimate the different parts of the mediation model that you have in the causal steps approach that we talked about earlier. Another thing is that most SEM software routines support convenient estimation of those asymmetric confidence intervals via the non-parametric bootstrap. So that's great. You know, you can just specify an option, and most of them, a lot of them, those packages will have an option to get the indirect effects, the total effects, the direct effects, and bootstrap-based confidence intervals. It's just like a simple option. A big one that I like is that latent variables can represent shared variance among multiple correlated variables for x, m, and or y. And this is particularly helpful for the mediating part of the model, the M, because it can reduce the impact of measurement error, thereby maximizing accuracy for testing indirect effects and assessing your mediation. So this is a way to address that assumption of perfect reliability of the mediator. You can have multiple less than perfectly reliable measures, and you can use their shared variance to represent mediation rather than just a single variable that we have to assume is measured with perfect reliability. And then another big advantage is that SEM can be used to fit a wider variety of models, including ones with multiple mediators and longitudinal mediation. So let's look at that next. So here are a couple of conceptual diagrams that you could fit very easily using SEM software. You can compute the total direct and indirect effects seamlessly. So in this one on the left-hand side, we have X leading to two mediators, M1 and M2. And you have paths A1 and A2 representing their effects of X onto the mediators. And then you have respectively B1 and B2 representing the effects of the two mediators onto the outcome Y. And then you have our old friend here, C prime, that is the direct effect of X on Y when you have these mediators in the model. Now over here on the right-hand side, it's essentially the same model, but what we've done now is we have introduced an additional pathway, this downward vertical arrow here that's labeled M1, M2. And what it allows you to do is have a causal flow that starts out at X, goes along the A1 pathway, hits M1, goes along this M1-2 pathway down to M2, and then travels along B2 and ultimately arrives at Y. So as you see, you can evaluate things like chained mediation. X leads to M1, M1 leads to M2, M2 leads to Y, while appropriately allowing for other effects to be estimated in the model. And so here's an example of this kind of chained mediation. Kyung-hee Choi, who used to be at the Center for AIDS Prevention Studies, Lisa Bowleg, and I fitted a mediation model with a latent difficult sexual situations variable measured by 3 correlated indicators. So the idea here is that they had an hypothesis that sexism would lead to psychological distress, which would in turn lead to difficult sexual situations. And that would ultimately lead to a report of having had unprotected sex. And what we see here in the results is that asterisking represents statistical significance. 1 asterisk is statistical significance at the 0.5 level. Double asterisk is statistical significance at the 0.1 level. You have sexism here with a positive and significant effect leading to psych distress. You have psych distress with a positive coefficient here, statistically significant, leading to sexual situations. And then sexual situations here is represented as a latent variable measured by 3 variables that were asked on the survey that they gave to women: trading sex for money, having sex while drunk or high, and having experienced some form of sexual coercion. So that's a way to address the imperfect reliability of each one of these 3 variables by looking at the shared variance and representing that as a latent variable in this mediation model. And then difficult sexual situations has a positive and significant relationship with unprotected sex. Now, one thing that's interesting about this model is you also have here a different pathway that you can take from sexism to unprotected sex. You actually have several. One here is from sexism to difficult sexual situations, bypassing psych distress, and that is statistically significant and positive. And then you have the same leg from the mediator to the outcome. So if you multiply these two coefficients together, you have a statistically significant indirect pathway this way too. So this model allows for multiple indirect pathways, which is kind of nice, right? It allows you to see different directions of relationships or associations. Now, there's another one, which is from sexism through distress to unprotected sex, and this psych distress to unprotected sex effect, that one is not statistically significant. It's very close to zero. So we would say psych distress does not mediate the effect of sexism to unprotected sex just by itself. It has to be involved here with difficult sexual situations, which is a theory-based construct that an investigator from the early days of CAPS, Rafael Diaz, had postulated. So that's just an example of one application of SEM where you can fit these more complicated mediation models.
Pardon me for breaking in. I have an excellent question from Nea Fatah-Menezes, one of our TAPS fellows. Nea, did you want to unmute and ask the question? I know we were talking about saving questions for the end, but this is really specific to this slide. And so maybe it'd be great to ask it now.
Sure. If Tori, you could go to the previous slide, I think it's a simpler example. So for instance, I see here that the two mediators, M1, M2 that you listed, and the potential sort of pathway from X to Y that can go through both is only going sort of unidirectionally, right, from M1 to M2. And my question was if you could have it go in the opposite direction simultaneously, or if that violates an assumption of temporal ordering, the assumption of temporal ordering that you had mentioned earlier.
That is a fantastic question. So the general answer is yes. The specific answer is no. So what I mean by that is in this specific model, there's not enough information to have two different arrows going. So like to add in an arrow going from M2 to M1, because that would be called a reciprocal effects model. And in SEMs, you can do that, but to do it, you need to have an additional variable sitting out here. Can you guys see my mouse pointer moving?
Yes.
If I circle, yeah. Mm-hmm. Okay, great. So you would have like another, let's call it X1. You would have an X1 out here pointing to M1, and then down here, you would have like an X2 pointing to M2. And those would be, those are sometimes referred to as instrumental variables. So you would have to have what are called like strong instruments of M1 and M2 in order to enable that to have bidirectional arrows. Otherwise, there's not enough information to have a bidirectional path there. Now, what you can do, and what I've more frequently done, if M1 or M2 are measured at the same time point, I will introduce a correlation between their residuals. So these diagrams are simplified. Technically, M1 should have a circle with an arrow pointing to it, and that circle would represent the residual variance of M1 that's left over after you've accounted for X. And similarly, M2 should have a residual variance term, like in any regression, right? When you fit X predicting, let's say M2, there's going to be what you've explained in M2, and then there's going to be some error variance that's left over. And then what you can do is if you have those two error variances, you can correlate them. And you can correlate the error terms with a bidirectional arrow that basically just says, hey, I think there's like shared variance between M1 and M2, but I'm not going to take a position on what the directionality of that is. And I'm going to show an example with longitudinal mediation in a moment that will actually have those bidirectional correlation of arrows built in. Did that help answer your question? Okay,
yes.
Great. You guys are asking great questions. So I don't mind being interrupted, especially when you guys ask such great questions. All right. So that example was cross-sectional, and I'm going to talk a little bit about some of the like pros and cons of cross-sectional mediation a little bit later. You know, there are definitely some issues there. But you can also use SEM for longitudinal mediation, and there's a Mitchell et al. Paper from 2013 that shows that if you incorporate additional information, if you have it from X, M, and Y, you can reduce bias that you would get from fitting a traditional sequential mediation model to your longitudinal data. So what do I mean by that? Well, if you look at this, and I can't show you on this diagram, but if you imagine like kind of taking two pieces of paper or something and blocking out X2, X3, and M3 in the upper right-hand corner of this. So like just kind of imagine these are gone. And then imagine that you didn't have M1, Y1, and Y2 down here at the bottom. If all you had was X1, M2, and Y3, that's just the traditional sequential mediation model that we looked at before. And people fit that model a lot, right? That's the most commonly fitted mediation model. But if you have this additional information, Mitchell and her colleagues, they're saying, well, why not use it to get better estimates of A and B here, the components of your indirect effect that you're going to use to assess mediation. So if you include what these pathways here from X1 to X2 and X2 to X3, we refer to those as autoregressive pathways. Same thing down here with Y, Y1 to Y2, Y2 to Y3. And then up here, you're introducing M1 to M2, and M2 to M3. So you're incorporating additional information here to help get better estimates of A and B, and then also here C prime. And that can help you do a more rigorous analysis with your longitudinal data if you have all this information available. So I didn't show the residual correlations in this model, but to keep it from being less busy, because the model you're going to see on the next screen, very busy, but it's going to show those residual correlations. Okay, so one of my colleagues from our early scholar training program back in the 2010s did an R01 study to examine whether an intervention that he designed for medical students in Puerto Rico could reduce HIV/AIDS stigma against people living with HIV. So we found a beneficial effect of that intervention, and that was great. And then he was interested a little bit later in trying to figure out, well, what could possibly explain this intervention effect? So what we have here is a variable called group, and that is indicating whether someone's in the intervention group or not. So 0 equals in the control arm, 1 equals in the intervention arm. So this is a randomized controlled trial with longitudinal data. And then he also collected some information on people's negative and positive emotions that they have about people who are living with HIV. And this particular model illustrates, looks at positive emotions as a potential mediator. And then down here, we have stigma, which is the outcome measure. And positive emotions was the scale score. Stigma was the scale score. So they are continuous, approximately normally distributed. And the interesting thing about, a couple interesting things about this model. First of all, we are correlating baseline measures of positive emotions and stigma. We are not correlating group. The reason why we're not correlating group is people were randomly assigned to group. So that by randomization breaks any association between group membership and these other baseline variables. You're removing potential confounding by randomization. So that's great. But the mediator and outcome at time 1, those could be correlated. And so we allowed them to correlate. And in fact, they were correlated. And then you have here wave 2, wave 3, and wave 4, mediators and outcomes, mediator, outcome, mediator, outcome. And to Nea's point, because these were measured at the same time point, T2, positive emotions and stigma, we introduced this double-headed arrow, which allows for correlation among the residual variance. So E1 stands for error number 1. That is the residual variance for positive emotions at time 2, once you've predicted it from positive emotion at time 1, group membership, and stigma at time 1. So what's kind of cool about this model is a couple of things. One, as I was saying before, you're going to get better estimation of the mediation effects because you're including all this additional information from the different waves of measurement, and you can correlate the error terms in here as well. And I hate it when this happens. So I had it right in my mind, and then it just flitted away. Let's see. So we talked about better estimation of the effects. We talked about correlated residuals. Let's see. Thank you, Natasha. I kind of looked at the chat because I was like thinking, oh, maybe somebody would be able to read my mind and tell me what I was going to say that was so beneficial about this. Well, maybe it'll come to me when we hit the next slide, which summarizes the results from this. So as I mentioned, we have 4 waves. Time 1 baseline, time 2 was immediately after the intervention, time 3 was 6 months post-baseline, time 4 was 12 months post-baseline. And we see this kind of design a lot in social and behavioral intervention research. And we were interested in the group effect, randomization status, whether it was positively associated with the positive emotions mediator at subsequent waves. We were interested in whether the emotions mediator at time t-1 was negatively associated with stigma at time t. So as your positive emotions about people living with HIV go up, there should be a reduction in stigma. And then the key indirect effect of interest was that we wanted to see the group being negatively associated with stigma at time t through the positive emotions mediator measured at time t-1. And so if you see this finding, which we did, your interpretation is that intervention participation increased positive emotions towards people living with HIV, and then that in turn reduced participant stigma towards people living with HIV. And we liked it better than regular sequential or serial mediation analysis because you can include those autoregressive pathways. And you can also, that's what it was. That's what I wanted to say. You go back here and you look, you can include these opposite effects, the opposite direction effects, right? So you can include the effect of stigma at time 1 on positive emotions at time 2, and the effect of stigma at time 2 on positive emotions at time 3, and so on. So it can help you basically control for any bidirectional effects that are happening. And we can do that because we have the longitudinal data and we have the temporal ordering. So that is a worked example of a longitudinal mediation analysis using structural equation modeling. However, and SEM is wonderful. I love SEM, but there are some limitations. So let's talk about them. The causal steps based on fitting multiple linear regression models and SEM-based mediation analyses both rely on some pretty strong assumptions. First, even if the participants were randomly assigned to X up here, right? So we talked about that in the last example. Or if all possible exposure outcome confounders are controlled for, there might be some mediator outcome confounding here, and that's represented by U because participants are typically not randomly assigned to M, right? So in that example that I just showed you, we didn't randomly assign people to have different levels of positive emotions, right? You just can't do that. There is possibility here of bias if you don't figure out what the potential confounders are and include them somehow in the analysis. You might represent here in this diagram, it might represent one or many variables that are observed or unobserved. So you might have some that are observed and that you measured them and you can include them to help reduce bias, and that's great, but you might also have some unobserved confounding too. All right, so uncontrolled confounders can bias mediation analysis results, just like They can bias regular regression results. And then you have another limitation, if that wasn't enough, you have another limitation of these traditional regression and SEM-based approaches, is that you have an assumption of no interaction between the exposure and the mediator. So in that example that I just showed you, we didn't assess, is it possible that there's some kind of interaction happening between randomization status and positive emotions? We didn't have an hypothesis like that, but hey, it could be possible, and we might want to check for it, right? So the other thing is there might have been some kind of interaction between X or M, the exposure and the mediator, and some other potential confounders like gender identity or something, or age or something like that. So really, ideally, we'd like to be able to investigate and account for those kinds of interactions if they happen to be present. So, and then our example, we had the fortuitous situation of two scale scores there. We had for M and for Y, so they were continuous and roughly normally distributed. But it really would be helpful because we often deal with variables that are binary or like very limited ordinal, they might be counts or something like that. It'd really be helpful to have some kind of general framework that allows us to have non-continuous M's and Y's, mediators and outcomes. So happily, we do have an approach that can do those things. It's called causal mediation, and it's an outgrowth of the more general causal inference framework. And I put down here at the bottom, there's a really nice paper in Psychological Methods by Valeri and Vanderweel called, it's like an introduction to causal mediation analysis for social and behavioral scientists. And it has a very clearly written intro that talks about the traditional approaches and where the causal methods go beyond them. And they provide SAS and SPSS macros, which is really nice. And then some colleagues of theirs created a user-written stata command called Paramed, and those can all be used to fit sequential mediation models. And Paramed turned out to be such a good command that in version 18, which is the most, well, maybe it was either version 18 or 17, I can't remember now. Might have been 17. Stata Corp basically took, for all you Stata users, they took the logic of Paramed and they created their own Stata Corp supported command called Mediate, which is very similar to Paramed. But it's always nice when things are supported by the vendor if you're using a commercial package like Stata. There are also various R commands, and Valente and colleagues in 2020 put together a really nice publication where they compare the different software packages and their capabilities, at least as of 2020. So I refer to this causal mediation approach as mediation 3.0. And it takes a different approach from traditional mediation models like regression and SEM. So rather than what those methods do, which is focus on estimates, parameter estimates from parametric regression models, or in the case of SEM, like regressions within a broader set of simultaneous equations, causal mediation methods invite us to consider a thought experiment. So in an ideal experiment, we'd like to randomize everyone to getting some kind of exposure, X, at level 0 of X, which we could call control, and level 1 of X, which we'd call intervention. And then if we assume an outcome Y, we'd also like to ideally be able to observe the value of Y at X equals 0, and we're going to call that Y0 here, and X equals 1, which we're going to call Y1. However, in reality, we can only randomize a given person to either have X equals 0 or X equals 1, not both. I mean, there's some you never want to say never, because there are some like little odd sort of or unusual exceptions to that rule, like completely within subject micro-randomized trials where you give somebody a message over their smartphone, and you might give them a control message at 10 o'clock and an intervention message at 4 o'clock, and you can do that many, many days in a row. And so then in that sense, people can be either in X equals 0 or X equals 1. But for most studies, you can only randomize people to have one of those states, but not both. So in that situation, then if you randomize somebody to X equals 0, and you observe y0, y1 you cannot observe. So it's referred to as a potential outcome or a counterfactual. And then you do the same thing for x equals 1. Some people get x equals 1, but the people who don't, y0 for them is a counterfactual outcome. Okay, but the trick here is that you can average across all study participants, and then you can compute a treatment effect as the expected value. That's what that E with brackets refers to as y1 minus y0. And then that's kind of causal inference 101. But then where mediation comes into this is the trick here is you can compute the same effect at different levels of a mediator M. So that's what gets discussed on the next slide here. So Valente et al. Really describe these in a very readable way. There are 6 of them. There are kind of what I would consider to be 5 of them that people use a lot, and one that's maybe used maybe a little less often that I talk about on the next page. On this page, there are the first 4 are a combination of indirect effects and direct effects. And if you think about the logic, I'll just introduce this by saying, if you think about the logic of, if you had a binary mediator and you had a binary exposure, then you could have 4 possible states, right? You could have both the exposure and the mediator having 0. You could have the exposure having 0 and the mediator having 1, and then you could have the mediator having 1 at the exposure being 0 and the mediator at 1 having the exposure at 1. So that's essentially what these first 4 effects are about. The first one of them is the total natural indirect effect, and if you look here at this expected value expression, you see it's at y1 m1 minus y1 m0. So that, in plain English, is the effect of x on y through m when the direct effect is held constant at x equal 1. Then you can do the same thing now, but what we're going to do is we're going to change y from 1 to 0, and that is referred to as the pure natural indirect effect, and that is the effect of x on y through m again. It's just this time the direct effect is held constant at the control level of x equals 0. So what we're doing is we're decomplicating the analysis here by fixing one variable to a specific level, and then we're able to estimate the effect of the difference at the other level. So continuing on here, you have the total natural direct effect. That is now where you're setting m to 1 for both states, but y1 minus y0. Okay, so that is a direct effect now. The effect of x on y when the mediation is held constant at level m equals 1. And then the last one is the same idea. It's just now we're doing y1 minus y0, but now we, instead of having m equals 1 as we did up here, we're having m equals 0. And that's the effect of x on y when the mediation effect is held constant at the control level of m equals 0. So once you have those 4 effects, you can then add them up to get the total effect. And there's an identity here where you have the total natural direct effect and the pure natural indirect effect. You can add them to get the total effect, or you can take the pure natural direct effect and the total natural indirect effect and get the same thing. Okay, that's a lot. You know, you can look at the Valente paper and it really kind of unpacks it in a very nice way. There is a 6th effect. It's less frequently used. It's called the controlled direct effect. And that is basically where you take the expected value of y at 1 minus y at 0, but you are fixing the mediator now to some level, some specific level. And that's very useful for answering what if policy type questions. So like if we were able to change this mediator capital M to some specific value, little m, what would the effect of x on y be at that point? And of course, if you're going to do that, you will want to set m to be some kind of meaningful policy relevant value. Now, causal mediation methods do still assume no unobserved confounding of the X to Y, X to M, and M to Y relationships. However, they do allow for the inclusion of observed confounders. And one thing that's very beneficial is that the causal mediation literature has developed sensitivity analysis methods to evaluate whether you have any remaining uncontrolled confounding. And there's a reference to this Kai 2022 paper for a worked example of that. There is off-the-shelf software for basic X to M to Y sequential models. There are examples published for other scenarios, and I give you one, Bind et al. 2016 for longitudinal data with an exogenous exposure. But really, for an extensive, deeper dive into causal mediation, Tyler Vanderweel has published a complete textbook in 2015, and he also has a bunch of articles. And actually, the book is really a compilation of the articles. So like each chapter is based heavily on published articles. You don't have to buy the book. You could go look at the individual articles, or the UCSF library has the book too. I know, like when I looked at it last time, it was at the Mission Bay Library, and they'd let you check it out for like 2 hours at a time, which is kind of interesting, but UCSF does have it. So let me now turn just briefly to a specific application of this causal mediation approach, and that is involving something called post-exposure confounding. The previous slides assume there's no post-exposure covariates that are affected by the treatment and in turn affect the mediators and the outcomes. But in an intervention setting, an intervention could affect a post-treatment covariate, which in turn affects one or more mediators. So one way to think about it is you have this treatment here to M relationship, but it's confounded by this treatment-induced confounder over here at the top. It can occur in observational studies as well. And one way I like to think about it is you've introduced a second mediator between the treatment here and M. So you have TX going to the confounder and the confounder going to M and the M going to Y. So one example of this is in Marian Kaiser's 2021 paper. They studied the relationship between parental job loss and children's subsequent behavioral outcomes. So their exposure here was job loss by the parent, and the outcome down here on the right is child's behavior. And you have mediators of interest were down here, family income, negative parenting. And then you have some post-exposure confounders up here at the top, including parental separation and whether the family moved. There's a command in Stata called RWR-Med that will handle this particular scenario. Because this is a relatively new technique, there are multiple analytic approaches that are being developed and presented, being tested for this approach or this type of model in the research literature. The Stata command implements something called regression with residuals, or RWR. Ariel Linden, who's in San Francisco here, wrote a community contributed Stata command called RWR-Med in conjunction with some folks at Stata Corp that can be used to perform those kinds of analyses. It can also estimate the regular, natural, direct, and indirect effects if you don't happen to have a post-exposure confounder, so that's handy. It can handle a lot of different kinds of mediators, so continuous, binary, count, but only continuous outcomes. So that's kind of a limitation. So let me just now turn to the last mediation topic, which is mediation, what I call mediation 3.1, and that's machine learning methods. So as I've been saying, we've been assuming for the most part no potential confounders of X to M and M to Y, except for that last little very specific example of post-exposure confounding. And we did comment that the RWR approach, which was implemented there in Stata, assumes continuous outcomes. So if you've got non-continuous outcomes, which working in health sciences we often do, or additional covariates W, which I've shown down here, that could affect the exposure mediator relationship, or U over here that explain the or affect the mediator outcome relationship, then you're in a more complicated situation. If you've got a relatively few number of covariates, you could treat these, or confounders, you could treat these as covariates and adjust for them in the analysis, like maybe in an SEM or something like that. But if you don't, it's going to be more difficult. For instance, if your collection of covariates in W or U here are high dimensional, and that's just a fancy statistical term for numerous. In other words, a lot. You got a lot of covariates, a lot of W's, a lot of U's, a lot of potential confounders that you've measured. What do? Well, one thing that you could consider doing is using stratification or inverse probability weights that are based on propensity scores to distill the effects of multiple covariates into some kind of single propensity score or inverse probability weight, and then apply that to the mediation analysis to essentially block or negate the effects of those covariates. And that approach is sometimes referred to in the causal inference literature as marginal structural modeling. And Valente et al. In 2017 has a nice paper for how to do this in the context of mediation analysis. But you can extend these propensity-based methods using machine learning methods because when you calculate the propensity scores or the inverse probability weights, most often like people use some kind of logistic regression model. You might include a bunch of main effects and interactions, but what if your data aren't particularly, they don't fit particularly well with the regression model, logistic regression model, for instance. So this is where machine learning methods can be very helpful. They unite rigorous approaches that are developed in the causal inference literature, such as AIPW, which is an augmented inverse probability weighting, with modern machine learning methods like stacked ensembles, which some of you may know as superlearner. The idea is instead of using one model to calculate your inverse weights or your propensity scores, you fit a bunch of different models like logistic regression, random forest, generalized additive model, all these different models, and the algorithm figures out the predictive power of each individual model, and it weights the prediction according to whichever models predict the data better than the other models. So you can get very good predictions with those methods, and then you can utilize that information, bring it back into the mediation analysis. So that's machine learning mediation. This is really a cutting edge of statistical research and application. I took a class on it back in August. Much of the work in the area is being done using R packages, some of which are available, but most of which I would say are in development. You can fit standard sequential mediation models using these, but it's also possible to hack R packages designed for dynamic treatment regimes. In other words, like a situation where you give somebody a treatment, then you measure their outcome, and then depending on what their outcome looks like, you either ramp up the treatment or you lower it or you switch to some other treatment. You can hack that package in an off-label way to investigate longitudinal mediation using these machine learning approaches. But it really requires a lot of skill and study. And when I took that class, which is awesome, and I put the info down here in the last bullet, one of my fellow students tried to work some of the examples in the class, and he was running into a lot of R issues, and I had to keep going back to the instructor and saying, okay, I got stuck at this step. Now I got stuck at this step. So if you're a person who's really good with R and you're good with statistics and you don't mind hacking R packages, more power to you. This could really be a viable cutting edge approach for you. But for the rest of us, we're going to be probably working with SEM for a while until some of those canned R packages are available that will be maybe a little more user friendly for us mere mortals. So just to wrap up on mediation, I just want to point out that we've been talking a lot about analysis, but there are some things you can do at the study design stage. So let's be mindful not to rush past study design to get to analysis. You can sometimes, and this is discussed in the Valente paper, you can randomize X in one study, and you can randomize M in a second study, and then you can try to put the results together to demonstrate that there's mediation. You can also, if you're really fortunate, randomize both X and M in the same study. And, one of these potential study designs is called MOST, the multi-phase optimization strategy, and kind of a neat design. It uses a factorial design to randomize people to either get or not get various subcomponents of an intervention, like that's a combination intervention. So my colleague, John Sauceda, Division of Prevention Science, he's doing a MOST. He's actually involved in several of these MOST studies, including one at the US-Mexico border with substance users where they're giving them methadone, but they're also giving them some behavioral intervention. And the MOST design, people are randomized to get different intervention subcomponents, and then they'll be able to tease apart which components were really most efficacious. But practically speaking, it is unusual to be able to randomize them. So at the study design stage, you want to carefully consider what potential confounders you have and measure them. You could consider including multiple measures of each of them to account for mediator measurement error. And another thing too that we haven't really talked a lot about, but you might want to consider timing of mediation. For instance, when to measure mediators. And then for that, your subject matter knowledge is important. So does an intervention, for instance, affect people very quickly, or does it maybe take a little bit of time for things to sink in? Cross-sectional analyses may yield biased results. There's that Mitchell and Maxwell paper from 2013 that talks about it. Some journals and reviewers will still accept cross-sectional mediation results as long as you state limitations around that, if you don't have temporal ordering, it's hard to draw really, causal conclusions about directionality of effects, but others won't. We've definitely had papers rejected from journals where they're like, we're just not going to take this because we don't feel it's rigorous enough. That's just something to keep in mind. All right, I'd like to pivot a little bit now and talk about moderation. Moderation is when the effect of one variable on another, say X on Y again, is changed by a third variable, which I'm going to call mod. And often, we see that in disparities research. It's often we've used race ethnicity. Moderation is sometimes called effect modification by epidemiologists and public health researchers, and statistical interaction by biostatisticians. The moderator can be continuous or binary, and the diagram at right contains a shorthand representation of what that could look like visually, where you have a regression model where Y is explained by X, mod, and the X by mod interaction term. Now, one critical limitation in moderation analyses is that usually you're going to need many more participants to have good power to test for interaction or moderation relative to testing main effects. And I include a reference there to this Leon and Heo paper. It talks about maybe needing 4 times as many, or maybe even more than you would just to look at main effects. So for this reason, in my experience, moderation analyses, like in grant proposals, are often proposed to be exploratory. Well, let's talk a moment about interaction patterns. There are different patterns that you can have. So I just made up a little toy example here. Let's say you're interested in assessing the mean energy level of people who are assigned male at birth versus female at birth, if you give them coffee or you don't give them coffee. So in this left-hand panel, there's no interaction because there's a 10-unit climb for both sexes when you switch from no coffee to having had coffee. On the other hand, over here in the middle panel, there's a crossover interaction pattern where for the males, you go from 10 units to 20 units when you're given coffee, but for the females, you drop from 20 units to 10 units when you've been given the coffee. And then over here is another potential pattern, one cell different. For the males, you have no coffee and you give them coffee and there's no change. The females start out at 10, but they climb to 20 when you give them coffee. So this cell up here, that's the one cell that's different, female and coffee. All the others have a mean energy level of 10 units. Now, there are also other possibilities, especially when you have more than 2 levels of each factor. You can also have continuous predictors that can complicate things. But the general rule is if the lines are not parallel when you draw out the means or the proportions, there's interaction present. But conversely, if those lines are parallel, there's no interaction. Now, there are different types of interactions, and the most commonly used one is a multiplicative interaction where you take X and you take mod, you take those two predictors, and you multiply them together to yield a product term that's included in the model, along with the X and the mod main effects. Now, when Y is continuous, a test of X times mod, that multiplicative interaction will yield this identical results to comparing the means directly at different levels of X and mod. But when Y is not continuous, when the outcome, in other words, is not continuous, for instance, maybe it's binary, that equivalence doesn't hold anymore. And thus, epidemiologists and public health researchers with binary outcome variables are increasingly interested in what are called additive interactions. And an additive interaction is essentially an interaction studied on the probability scale rather than on the log odds or log risk scale, that the kinds of results that we get from a logistic regression or relative risks type of model. So Vanderweel and Knoll have a really nice in-depth published tutorial on this topic. And then Melanie Wall has a readable online introductory slide deck to get up to speed on it quickly. Now, one thing that's really interesting for health equity researchers is this idea of many intersecting levels. So the health equity field is increasingly considering how intersecting memberships in many categories and identities and lived experiences can affect health outcomes. This is sometimes referred to as intersectionality research or intersectional identities research. We can find value in describing which combination of intersecting identities and lived experiences best explain various health-related outcomes. So the problem from an analytic perspective with this is that it can lead to regression models that have main effect terms with many levels per term and interactions then that are even worse because they're products of those main effect terms consisting of so many categories and so many levels that ordinary regression models tend to break down and have poor statistical performance. I mean, even with pretty large samples, 2,000, 4,000, 5,000, and most of us aren't in the fortuitous position to have those kinds of samples. So Meyer Menhendren and Greta Bauer conducted a simulation study comparing regression models with all possible interactions to various alternatives, including several machine learning-based approaches, such as decision trees and random forests. And what they found was that random forest and a tree-based approach called conditional inference trees tended to outperform more traditional regression methods and early classification and regression tree approaches. I know Nea, for instance, is using conditional inference trees in one of her projects right now. So it's exciting, you know, that these machine learning methods are beginning to seep into some of our more traditional moderation and mediation spaces. You can also combine mediation and moderation. Amanda Fairchild has a nice paper from 2009 that talks about that. You can have mediated moderation when some kind of interaction here represented down here in the lower panel figure is mediated by a mediator. So the X to mod relationship, the interaction is mediated by M. Now, on the other hand, you can have the moderated mediation when you have some kind of indirect effect here, X to M to Y, the A and the B paths are themselves modified by mod. Okay, so you can do that as well. I have an example from Orlando Harris, who's a former postdoc at CAPS and in the School of Nursing. I'm going to go through this pretty quickly because I know we're starting to get close to time here. But again, it's just another applied example to kind of give some life to these concepts. He was very interested in contextual factors that might affect individual factors, which then affect COVID vaccine uptake in older African Americans here in the US. And so he's got this long list of potential contextual factors here on the left-hand side, and he's got an equally long list of potential individual factors here, which leads to a binary vaccine uptake factor. So if you think about how you could analyze this, you could look at everything together if your sample is big enough using structural equation modeling, or you could look at specific pieces of this, like do social networks affects social support, which then in turn affects vaccine uptake. You can sort of zero in, do a more concentrated look using sequential causal mediation modeling. And here are some additional thoughts about that, some potential models that he could consider fitting. Over here on the left-hand panel, you have social networks leading to social support, and social support leading to vaccine uptake. Over here on the right, kind of similar idea, but it's maybe a little more complicated. You have a latent M1, latent mediator health measured by health status and lifestyle behaviors. You have a latent psychosocial mediator measured by a social support variable and various psychological variables. And then you still have social networks as the exposure and vaccine uptake as the outcome. You could use SEM for something like this. You could use the causal mediation framework for something like that. And then you could also consider moderated mediation. You might have a participant's age affecting the linkage between social support and social networks on vaccine uptake, and the mediational relationship here could be affected for people at different levels of age. And these are just a few illustrations. You have many different possibilities that you could consider. So let the temporal ordering, the availability of the data, what type of confounders you might have, and your research questions guide you for setting up these models.
Sorry,
Yep.
Before you go on for that particular slide, if you don't mind bringing it back. Yes. There's a question regarding the effect of X on, yes, there you go. Effect of X on M or M on Y. Go ahead, Nia.
Hi, Tor. More questions for me. So actually, you could go to the slides that you had, Orlando's analysis. One more forward. Yes. So my question was for the moderator here, age. Is it possible to have two different moderators that you are assessing? So for instance, you think age moderates the sort of association between social networks and social support, but something else like, I don't know, gender moderates the effect between social support and vaccine uptake?
Probably.
Okay.
Yeah, I'd need to think a little bit about what that would mean for the indirect effect. I mean, that's a really interesting question. But I think you probably could.
Okay.
Yep. Okay, I just wanted to close with a few resources and conclusions. Funny how we allowed an hour and a half and I still have only 5 minutes left. How does that happen? It's a kind of Parkinson's law, I think, of presentations. Anyway, thanks to you all for bearing with me for what turned out to be a longer presentation than I anticipated. So Steve Gregorich, who has been at UCSF for many years, did a couple of talks for the Center for Aging in Diverse Communities in 2014. One's on mediation, one's on moderation. I really like those two presentations. They provide a little more depth to non-causal mediation and moderation. The causal mediation software comparative review article that I mentioned before also has very clear definitions of the causal mediation effects, is Valente et al. 2020. If you're interested in learning more about the causal mediation methods and you're coming from more of the traditional approach, check out Valerian Vanderweel's 2013 article. And then Tyler Vanderweel also has tools in a free video. He has links to a day-long course that he taught in 2015 on his website. So that's neat. And then he also teaches a class from Statistical Horizons. Edwin and I both took it a few years ago, and it's really terrific. He has turned it into an on-demand 4-week period, so you can kind of do it in small doses. And there's a question and answer forum on Slack where he can answer people's questions and interact with the participants. And he does software demos in SAS and Stata. And then study design, you want to consider options for randomly assigning mediators as well as exposure whenever possible. So MOST, I gave that example. And anyone who's interested in MOST should reach out to my colleague, John Sauceda. He's like the MOST king who I know here at UCSF, and he's always interested in talking about MOST. When you're incorporating non-randomized mediators, though, consider that measurement timing and measuring confounders. For the sequential X to M to Y models or models with post-exposure confounding, consider these available off-the-shelf causal mediation methods, especially if you have non-continuous M's or Y's and or interactions, especially exposure mediator interactions. If you've got a lot of covariates or a lot of potential confounders for X to M or M to Y, you might check out those machine learning-based causal mediation methods. But I would say either be smart or find somebody really smart who's really good with R who can collaborate with you for those. And for those multiple mediator and longitudinal scenarios, you can look for the new causal mediation options as they become available. Otherwise, parametric SEM can be an accessible approach right now, as long as we acknowledge the assumptions and limitations. And then if you plan to test moderation by race, ethnicity, or another categorical variable, just keep in mind you'll need sufficient N for the various groups, and machine learning methods may be useful to identify key intersections. And that is it. I want to thank you all. I can take questions, and I can also stay over if people want to do that, but I'm also happy to take questions and then via the chat, and then compile a Word doc that can be shared later when we send out the slides.
Thank you so much, Tor, for that outstanding presentation. We really appreciate it. We had one question in the chat from Dr. Danish. Would you like to ask the question yourself? This is about propensity scores.
I just want to mention that I always thinking that propensity score matching is when we have two continuous variables. We want to do the matching at the beginning of designing a study, and probably Tor was talking that we can do something like that to handle the situation in the analysis level. That's I want to mention.
Yeah, I mean, I don't consider myself an expert on propensity scores at all. But what I remember so there's this fellow at Emory, David Benkesser, who taught the machine learning mediation course, and essentially, he was trained in the causal inference framework, including doing a postdoc at Berkeley. And basically, a lot of what he covered in that class is using propensity type models to create augmented inverse probability weights that you then apply to the mediation model to block the effect of measured confounders on the mediational pathways. So it's a very propensity score-ish like thing. It might not be exactly propensity score matching, but it's that kind of logic.
Yeah, thank you.
Mm-hmm.
Wonderful. I think we're just about at the hour. And we, again, really appreciate your education. It was an outstanding presentation. And as indicated, Dr. Neilands will be available through either email or direct contact for additional questions. Thank you very much.
Thank you all. Really appreciate it. Really appreciate the great questions, and thanks for sticking with it. I know it was a lot. But hopefully review the slides and it can help, and feel free to, as Mandana said, to contact me with any follow-up questions.
Thank you.